Welcome back to Economic Game Theory. I'm SSYOK. A quick thought experiment. Imagine you are playing a coin game against someone who always plays heads. What do? You play tails every time. And you win every round. Now flip it. If you always play heads, you get exploited. Any pattern you repeat, a smart opponent learns and punishes. Episode 4. Mixed Strategies. How to be strategically unpredictable. Let's make this precise with the simplest possible game. Matching pennies. Two players each secretly choose heads or tails. Player 1 wins if they match. Player 2 wins if they differ. The payoff matrix looks like this. Check every cell for a Nash equilibrium. At heads. Heads. Player 1 is happy. They matched. But player 2 wants to switch to tails to differ. So this cell is not stable. At heads. Tails. Player 2 is happy. But now player 1 wants to switch to tails to match. Not stable. At tails. Heads. Player 1 again wants to switch. Not stable. At tails. Tails. Player 2 wants to switch back to heads. Not stable. Every single cell has someone who wants to deviate. There is no pure strategy Nash equilibrium. So what should you actually do? Think about it from player 1's position. If player 2 always plays heads, player 1 should always play heads to match. But then player 2 should switch to tails to differ. But then player 1 should switch to tails to match again. And so on. Forever. Every fixed, pure strategy invites retaliation. The moment you commit to one, the opponent adapts. And you lose? The only way to stop this chase is to be genuinely unpredictable. Not bluffing. Genuinely random. In a way your opponent cannot detect or exploit. A mixed strategy is a probability distribution over your pure strategies. Instead of committing to heads or tails, you play heads with some probability p and tails with probability 1 minus p. You literally flip an internal mental coin, weighted by p, and play whatever it says. Your opponent knows the probabilities you are using. They cannot know the actual outcome of any given round. Because neither can you. This is what makes you unexploitable. Randomness you yourself cannot predict. Now the real question. Which p? You could play heads 70% of the time. Or 30%? Or 50%? Which mixing probability is the stable one? The Nash equilibrium. Here is how to think about it. Suppose player 2 is deciding whether to play heads or tails. If heads gives player 2 a higher expected payoff than tails, player 2 will always play heads. And your mixing becomes irrelevant. If tails is better for player 2, same problem in the other direction. The only way both of player 2's options are equally attractive, neither exploitable, is if player 1 mixes at exactly the probability that makes player 2's expected payoff the same. Under both choices, that is the indifference condition. Let's derive it in matching pennies. Player 1 plays heads with probability p. Player 2 is choosing between heads and tails. Calculate player 2's expected payoff from playing heads. If player 1 plays heads, probability p. Player 2 loses. Payoff minus 1. If player 1 plays tails, probability 1 minus p. Player 2 wins. Payoff plus 1. Expected payoff from heads. P times minus 1. Plus 1 minus p times plus 1. Which simplifies to 1 minus 2p. Now tails. If player 1 plays heads, player 2 wins. Plus 1. If player 1 plays tails, player 2 loses. Minus 1. Expected payoff from tails. P times 1. Plus 1 minus p times minus 1. Which simplifies to 2p minus 1. Set them equal. 1 minus 2p equals 2p minus 1. Solve. P equals 1/2. Player 1 must play 50-50 to make player 2 indifferent. By symmetry, player 2 also plays 50-50. That is the mixed strategy Nash equilibrium. Notice something strange about what just happened. We found player 1's equilibrium mixing probability by solving for player 2's indifference. Not player 1's payoff. Player 1 is not mixing to maximize their own expected payoff. Player 1 is mixing to close the door on Player 2's ability to exploit them. And here is the payoff. In equilibrium, Player 1's expected payoff is the same no matter what Player 1 actually plays in a given round. Both heads and tails give the same expected result. That indifference is not a side effect. It is the definition of what an equilibrium means in mixed strategies. Now let's apply this to a richer example. A penalty kick. The striker chooses to shoot left or right. The goalkeeper dives left or right. Simultaneously. Independently. The striker is right-footed. So they are better at shooting to the right. The keeper knows this and is therefore better at defending to the right. This creates an asymmetric payoff matrix. The striker's goal probability is not equal in all cells. Check for pure strategy Nash equilibria. If the striker always shoots right, the keeper always dives right, and the striker should switch to left. If the striker always shoots left, the keeper should switch to left too, and then the striker should switch back. Again, no pure strategy equilibrium. Both players must mix. The equilibrium mixing proportions in the penalty kick are not 50-50, because the payoffs are not symmetric. To find the striker's equilibrium mix, we apply the indifference condition to the goalkeeper. The keeper must be exactly indifferent between diving left and diving right, meaning the striker's mix must make each dive equally likely to succeed. Plug in the payoffs and solve. The striker shoots to their weaker side, left, more often than intuition suggests. The keeper dives to the strong side, right, more often than intuition suggests. The exact proportions depend on the payoff numbers. What both sides are doing is removing each other's incentive to exploit. Real football data confirms that professional players mix close to these theoretical proportions. Not because they know game theory, but because evolution and repetition select for unexploitability. So let's state clearly what has happened. A mixed strategy Nash equilibrium is a set of mixing probabilities, one per player, where each player's mix makes every other player indifferent between their pure strategy options. No player can improve their expected payoff by changing their mixing probability, because the opponent is already indifferent. They gain nothing from deviating either. The mutual indifference is the stability. This is exactly the same definition as pure strategy Nash equilibrium. No player can profitably deviate. Applied to the extended strategy space of probability distributions. Let's prove that last claim. No player can improve their expected payoff by changing their mixing probability. Let's look back at player 1 in matching pennies. In equilibrium, player 2 is mixing 50-50. Suppose player 1 deviates from their equilibrium 50-50 mix and decides to play heads 90% of the time instead. What happens to player 1's expected payoff? If player 2 plays heads, which happens 50% of the time, player 1's payoff is 1. If player 2 plays tails, also 50% of the time, player 1's payoff is -1. So player 1's expected payoff is half of 1 plus half of -1, which equals 0. Exactly the same expected payoff as mixing 50-50. Once player 2 is playing the equilibrium mix, player 1's expected payoff is completely flat across all possible strategies. Deviating gains you nothing. This brings us to a remarkable mathematical result. John Nash proved in 1950 that every finite game, any game with a finite number of players and a finite number of pure strategies, has at least one Nash equilibrium. It may not have a pure strategy equilibrium, as we have seen, but it always has at least one mixed strategy equilibrium. Nash's theorem is what makes the Nash equilibrium concept so powerful. You are never left empty-handed. If pure strategies fail, mixed strategies always provide a solution. 3 things to keep in mind. First, the indifference condition is derived from the payoff matrix as given. But real payoffs are hard to measure. A goalkeeper's estimate of the striker's left foot weakness is itself uncertain. Second, mixed strategy equilibria assume each randomization is independent across rounds. In a real penalty sequence, Players may update based on patterns, which is exactly the opposite of genuine mixing. Third, mixed strategy equilibria can be fragile. A tiny payoff change shifts the equilibrium proportions, sometimes dramatically. The framework is powerful, but it models idealized rationality, not psychology, learning, or fatigue. So game theory now covers two answers to strategic interaction. When one strategy always dominates. Episode 3. When no strategy dominates and mixing is the only stable response. This episode. But we have been assuming throughout that the game is played exactly once. What if the same two players face each other again and again? Something changes fundamentally. Reputations form. Punishment becomes possible. Cooperation can emerge. Even in games where it looked impossible in the one-shot version. That is repeated games. Episode 5.